The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
We're going to talk about the Wigner distribution function in integral imaging. Yeah. So I'm going to start with a description of what a conventional camera does. A conventional camera produces one view of something, does a pretty good job of imaging within a small range of distance from the camera, depending on how you focus it. And what we can do is create optical systems which allow the image sensor to capture multiple views. So basically, let's say you have an array of tiny cameras that share one image sensor in the back. And one way of doing this is to use a pinhole or micro lens array. So think of the pinhole cameras of yore. Now just have an array of pinholes, and you will get multiple pictures of the same scene. Okay, so conventional camera, what it does is, so this is a plot of x versus theta for what the sensor picks up. So for each pixel, it'll pick up the incidence rays for the entire range of whatever rays focus to it. So if you look at the blue lines, it'll pick up all the rays in that entire range of angular frequency, or sorry, spatial frequency, angular range, and integrate it in the form of intensity in that pixel. And so you lose all sense of angular resolution, so we have no sense of how far something is. If we did know what this range was, we could kind of say, well, if it's a smaller range, it'll be further away. If it's a larger range, it'll be closer to the camera. Okay, so we have these optical systems which trade some spatial resolution for angular resolution, and these two extra dimensions of recorded information allows us to reconstruct the original trajectory of rays to an extent. And things you can do with this is digital refocusing, which means you take a picture once, and then you can focus on different parts, different objects within the scene afterwards, just purely by processing it. And 3D imaging the scenes behind obstructions such as foliage or murky water. And since you also have a system which allows you to select for a location in space as well as an angle of propagation by selecting just a location in space, you could use the system reverse to kind of project 3D displays. Okay, so there's two common setups to do this sort of thing. The first setup is the integral imaging camera. Newer setups use a micro lens array because it allows you to gather more light at once, but you can also think of it as just a pinhole array. And at each of these pinholes, imagine if you put a little tiny eye there, so you'll be seeing the scene from several different aspects. So you get, in the image, the sensor picks up several copies of several pictures of the entire scene from many different perspectives. The Lightfield camera is a little bit different. You have a large convex lens focusing onto the micro lens array and a sensor plane shortly thereafter. Each of the tiny pictures in this case is a picture of a small part of the original scene. But each pixel within that tiny picture is a different view of that small part of the scene. So if this is kind of confusing, you'll probably see later on it'll make more sense. And with that, these two methods of basically splitting up the scene and to have some sense of angular resolution by splitting up how different rays with different angles will propagate to the sensor are essentially do what a Wigner distribution does. They're physical systems which perform a Wigner transform, which we'll talk about next. Michelle? Yeah.
Thank you, Michael. Hi, everyone. Today I'll be talking about two main concepts, which is the Wigner distribution function and the Wigner distribution function and the Lightfield. The Wigner distribution function, it is a function that describes a signal in space x and spatial frequency u at the same time. So the equation there is just showing a Wigner distribution function. Though this function, it gives the local frequency spectrum of the signal. Compare this to a Fourier transform, which gives the global frequency spectrum. So a Wigner distribution gives a localized frequency spectrum. And why do we want a Wigner distribution function? It comes in useful because sometimes it gives us extra information compared to the normal Fourier representation. So to illustrate this, I'll talk about signals where the frequency changes with position x. An example of this signal is a chirp function. The picture of a chirp function you can see in here, the left picture here. Its frequency changes linearly with position x. If you get the Fourier transform of the if you get the Fourier transform of the chirp function, it is a symmetric function which doesn't really give you much information about the signal. If you do a Wigner distribution, what you get is the picture on the right. You get a line, straight line, which shows you the frequency increasing with position x. Next slide, please. I was talking about the Wigner distribution function, which was derived from Fourier optics. Relating to this is the light field, which we can think of in terms of ray optics instead. The light field is a representation of the light flowing along all rays in free space. And a ray can be parameterized in multiple ways. For example, it can be parameterized by coordinates of two planes. And when one of these planes they're at infinity, then you can parameterize the ray by a point and an angle. In wave optics, on the other hand, you parameterize, you describe a wave in terms of spatial frequency and angle. And if you remember, spatial frequency u can also be thought of as angle theta over lambda. So this is how wave optics relate to ray optics, because ray optics, you think of it in terms of angle and position. Fourier optics, you think of it in terms of spatial frequency and position. Next slide, please. The Wigner distribution function, which is derived in terms of Fourier optics, gives a link between Fourier optics and geometric optics. It is described in terms of spatial frequency and position, but it closely resembles the ray concept in geometrical optics, which describes the ray in terms of angle and position. And I'll pass it back to Lei.
Okay, finishing about the mathematical description of space and frequency domain. I'll first talk about the sampling issue in space frequency domain. So basically, just to give you an idea why this system can give you samples in both space and frequency direction. So you can see from this figure here. So because the microlens array is you bought them or you put inside of your system, so you originally have the coordinates of all the microlens array. So this gives you sampling of the coordinates in space domain. Then each of the sub-image here shows here there's 3 rays. So each of the 3 rays gonna goes to different pixels on the CCD screen. So each of these 3 gives you, you can think about that on the sensor plane, it's gonna give you the angular information or the spatial frequency information because it's gonna goes to different pixels. So here is the simulation of after after several points from the object goes through the system, what it's gonna look like on the sensor plane. So one of the things you might notice that it's, for example, for this one, this is on one point. So the x coordinate actually is this one. So the center of this one, which is the x coordinate of the corresponding microlens. But if each of these segments, which is the 1 pixel, its sample gives a sample of the of the angle. Okay. So using with this data, what kind of thing we can do? The first thing we can do is called digital refocusing. So basic idea is if we want to take a picture of a 1 point, before Michael talked about the conventional camera. So what conventional camera does is, so given a point, you want to form the point, so you want to form the image of the point. What the lens does is, so it integrates all the rays, go to a point, and the corresponding pixel pick up all the rays from this point and add them together. So same idea. So given this point, because we have all these samples, so we add them together. Then we're gonna recover this point. So this is at the with this we call it in focus point, which is when the image is right at the microlens array plane. This is a 1D case, so when you add them together, maybe you're gonna get something like this. So the next one is one of the interesting thing we can do with the system is, so before you can imagine the previous slide shows the image plane at image plane of number 1 image plane. So here you have the image. So we want to know if we assume there's another image plane there at image plane 2, what's the image gonna look like? So the basic idea is, if you think about this problem in ray optics, given a ray here, the intensity gonna conserved. So which means the intensity at this point and at this point is the same. So using this geometry, you can work out the coordinate relationship. So you will find it's basically x before. So this thing shows this before we assume the shape of the signal with recording in the Wigner domain, or the x and space and angle domain. It's something like this shape. It only gives you a x sharing, which is in the apprentice. You see it is u is fixed, but with a new x coordinate, it's gonna be x plus something. Then you want to get some nice image, then you integrate with all the angle given x. Then you get the new image. Another thing we can do is, I call it 3D imaging. Actually, it's just like you can imagine, because you have all these microlens arrays. So it looks like you have different views. So how do you get different views from the system? So basic idea is, because we have all these samples along the angle direction. So for example, from this line, you pick up all these pixels. then you form image, right? So from this angle, the same thing for other cases. So actually we have set up a system. So this is a raw image we took. So you can see from this small thing, you can think about it as a micro lens. Each of the thing is micro lens. Also, Michael briefly mentioned that it's also a sub-image of the big field lens in front of the micro lens array. Either way, you can. It's okay to understand this issue. So some parameters with the system. So the diameter of the micro lens is 125 micron. The pixel size is 2.2. So you divide it. So you use the diameter of the micro lens divided by the pixel size. So in the maximum, geometrical sense, optic sense, you can have about 60 different views. But if you're taking the diffraction effect into account, actually we can only get like 9 to 10 different views because you cannot get a perfect one-point image. Okay, so this is one of the simulation results we get. So because it's a very low resolution result, because the micro lens array each of the size of the micro lens is too big. So the original the size when you extract doing the along this line, if you remember what I mentioned, it's only a 24 by 24 image. But if you can, yeah.
They're not really linked.
Okay.
Yeah. Maybe time for a quick question.
Yeah.
So if each subaperture focuses onto sort of a subgroup of pixels, what are the requirements on your sampling for each subaperture? Like, are you kind of like Nyquist sampling, or are you oversampled or undersampled? Obviously, your result will depend on how that sampling occurs for each subaperture. So how did you set the number of pixels per subaperture?
This is gonna involve with how to optimize the system. Honestly, I haven't go through this derivation, but intuitively, like you said, you can think about the point spread function of the system. If the point spread function is, say, so what? If you can imagine the limit case, if you have like 100 views, or in our case we have 60 views, but only 10 of them can distinguish, which means your point spread function is larger than your CCD size. So you might want a larger CCD size, which means under each micro lens you can afford smaller. You can afford less micro lens.
I think the question was, how do you sample the angular distribution, right? So after each micro lens, you have arrays that come out, and what is the sampling requirement there? Singapore?
Maybe as Lei was pointing out that basically we sample the space with micro lenses. So your sampling in the spatial domain is equal to the size of the each micro lens, and then behind each micro lens you put some pixels of CCD. So you can trade off. So you have got some total amount of resolvable information, which is given by the diffraction limit, and then you can choose how much of that angular resolution you want and how much spatial resolution you want. So if you wanted a higher spatial resolution, you would reduce the size of microlens array, and then you get higher spatial resolution. But in that case, you can only have only few pixels behind per microlens, and then that would make coarser angular resolution.
Another way to think
So,
about this
yeah.
is that the reason you sample the space behind the macro lenses is because in general you want to determine the slope of the Wigner distribution. So there was this nice example of a chirp, right? So the chirp in Wigner space becomes a slope. So you have to space your pixels in a way that you can resolve your minimum desirable slope, that is your minimum desirable chirp. And the chirp is very important because in optics it represents the focus, right? So if you want to do something like the 3D imaging, then each plane that you want to resolve corresponds to a different slope of chirp. So then the depth resolution that you want to achieve is actually limited by your ability to sample behind the lenses. So you see that you have a very nasty trade-off because your camera has so many pixels, right? So then if you make your micro lenses small to get good spatial resolution, then you get poor angular resolution. Of course, ideally, you would like to have a camera with billions of pixels. Okay, I think in the interest of time, we should move on. Thank you, guys.